a little bit in my field, but other than that, but it is, I think, a fertile area for researching other things.
Yeah.
Hi everyone, thanks for coming to the second NetSeminar. Just a logistics thing, the next NetSeminar is in 2 weeks on a Tuesday, which is written on the top. So today our speaker is Jonathan Perry from MIT, and his advisors are David Riksha and Hari Balakrishnan, and he works on resource allocation in data centers. And he recently joined us at Stanford to finish his thesis with our work. And okay, over to you.
Thank you, Lorana. Hi, everybody. Good afternoon. Today I want to talk about Flowcube. It's a scheme for data center resource allocation. Let's start. Oh, yeah. Great. So a lot of our applications have been moving to the data center, and in the past few years. And response time is kind of a crucial measure in order to get good user experience. Response time is important for user productivity. So imagine you're doing this operation with kind of interacting with your software, and it takes a second every time you click. And then sometimes it takes 10 seconds or 50 seconds. It's very frustrating. If you're talking about commerce, this translates directly into revenue, kind of clicks on ads or product purchases. And with software as a service as a whole, it's really important to get a very good user experience, so people use your software, not competitors. But there's another trend in data centers, and that is breaking up the applications into these tiny pieces, microservices. So the advantages are huge because you can develop each of the services individually. You can have a different software team, develop it individually, deploy it individually, scale it individually. But the problem is that as you move to this container architecture or microservice architecture, the problem is the network becomes crucial in getting good performance. So bad performance from the network translates to bad performance from the user. The Google's tailored scale argument. So what we set out to do with Flowcube is answer this question: can we give tools to our application developers or to our DevOps people that allow them to control how the network allocates resources? And the scheme has to be explicit. So the user needs to should be able to tell the system exactly, the network, exactly how to allocate resources, and the network should do it. It should converge very quickly and consistently to the right allocation. And ideally, we'd be able to do this in software. So if we come up with a different scheme of allocating resources, we can implement it. So this is what this talk is about, coming up with this type of network resource allocation. By the way, please ask questions as we go. Let's make it interactive.
So why do you think that explicit allocation will maximize utility? If you look at, things like, I don't know, compilers, right? In the bad old days, like humans would do register allocation. A compiler comes out and do it a lot better than you can. So why do you think that the programmers are going to do better than some algorithm for resource allocation?
Right. I don't think the programmers will do better than an algorithm, but we need to give the tools to the developers to write these policies. An algorithm should implement the policy, but the policy should be explicit. It shouldn't be something like, let's run TCP on it. TCP does something, and I'll talk about that. So what are we doing today? Our current resource allocation approach, congestion control and queue management, is packet by packet scheme. So we have these switch algorithms that we write. So a packet comes into a switch. We write these advanced queuing management schemes. So do I drop this packet? Do I drop another packet from the queue? Which queue does the packet go into? And we write server algorithm. So this is TCP, right? TCP, DCP/CP, and here we get a packet. It's either marked or it has an ACK or some kind of with a gap. How do we react to it? Do we increase our rate? Decrease our rate? So it's all reactive per packet. The problem is that the allocation is implicit, and we're writing these distributed algorithms and want to get a behavior from the system that conforms to what we want, but we write these tiny pieces of it. It's really hard to get the right emergent behavior. Another thing is the data that each of the points, the nodes in your network gets, either the servers or the switches, is very partial and noisy. So you get, if you're on a flow, you only get congestion notifications for what happens on the same flow, not what happens inside the network usually. And switches have to average their traffic over a period of time in order to understand changes in the network. So this reacts very slowly, has this dependence on round trip time in the network in order to convert to the right. And in order to deploy a new system, you have to change many components. So traditionally, you have to change all the switches if you want to change the switch algorithm. You have to wait for new hardware to come out and then physically replace the switches. On the servers, you have to deploy algorithms to all new operating systems to all the servers, which is also slow. This is becoming easier with the advent of programmable switches, like the barefoot switch at P4, where you could just reprogram software on your switches, but still, it has the other disadvantages. And you have to, it's a distributed problem. So you have to distribute your code over the entire network in order for it to work. Code distribution. So what did we do with Flow2 in order to get the properties that I talked about earlier? So first, we noticed that in many data centers where you can allocate based on flowlets, and by flowlets here I mean a collection of packets that are share an operating system queue, a send queue in one of the servers. So if you have a flow in the network, let's say you have a network, as long as the active flows remain the same, your allocation should remain the same. An example is, let's allocate 10% of traffic to one of them and 90% to the other, or let's prioritize, strictly prioritize one over the other. And this allocation would remain constant throughout the life of these flowlets until something happens. So either a flowlet arrives or flowlets leave the network. Okay, so with this property, you can schedule just when these events happen. Yeah, question.
So there's the difference between flowlet and the traditional flow. That a flowlet has also a window of time of the time.
It's a burst of packets. Yes. So kind of traditionally, there is another definition for flowlet that we're kind of overriding here. Usually, a flowlet is this burst of packets inside the network for the same flow. Here we're talking about application level flowlets. So a batch of packets. So if the application is calling send on a socket with a megabyte, we call that flowlet. Or if it's calling, kind of, as long as these packets wait in the same queue, we call them a flowlet.
If I was flow controlled by TCP within the same application, then slowly you're going to receive a different flow. So
Every time the window opens, no. So every time there's a send socket call, we kind of treat that as a. And in many applications, these send socket calls are also an application data units. And we want to send all of this to the other side, and the other side needs to keep all of it before it can process. Many times, not all of it. So it makes sense to treat them.
So is that the definition of flowlet?
Sorry?
Is that the definition of flowlet? A block of data that is emitted through send socket call?
Yes. I mean, we have a more refined definition where it's a batch of packet that is waiting in the queues, and you treat multiple of these as the same flowlet if there isn't a gap more than a threshold between these batches, let's say 50 microseconds. So as long as the queue is not empty for more than 50 microseconds, we call this flowlet.
But do they all belong to the same application?
They all belong to the same flow.
Yeah. It doesn't like you found. It doesn't like you get.
Right. Yes, you can define either depending on what behavior you want to get. I think it's not as important to what I'm talking about. Yeah.
This is a burst within a flow.
It's a burst within a flow. Great. So this is the first
I have
observation.
a question. So when
Yes,
it starts, you don't know the size of the flow yet.
When you start, actually, you do know the size of the flow because I mean, when it starts, it depends on which definition you use.
Yeah.
But
Okay.
if you look at the send socket calls, you know, you know lower bound. You know the minimum number of packets.
Do you use that information?
Not in this
Okay.
setup, but you could. The other observation that we've made is that if we want to have the system converge very, very quickly, we want to eliminate as much as possible the dependence on round trip time in the network. We don't want to have kind of these averaging behaviors. We don't want to create mechanisms that react after an RTT. So they tweak the network and then react after an RTT. So we want to centralize the allocation. And this is good. This also helps with deployment. So if you want to change the scheme, you need to only change your central allocator. Centralized resource allocation. So let me run through an example to make this more concrete. Let's say you have Hadoop running on some server A and it has some data for a node B. Starts the connection from A to B, a TCP connection. And in parallel, it contacts the allocator and tells it, I'm Hadoop, I have data for B. The allocator has a view of what's happening in the network, so it allocates according to policy and tells A to send at some rate. So here it could burst at line rate because there aren't any other flows. So there you don't have to go through flow start, burst away on network. Now a new flow comes in from ads on server C for B. Ads has higher priority. It opens the TCP connection. So there's
Say how much data A has.
You could, but here we kind of do this abstracted again. Just that there is a flow and there's data.
So there's going to be a time window that the person go out then, or
right now what we do is we have these on and off events. So the server says, now I have data, now I don't have data.
because yeah, we're going to okay with the mutual results for particular time.
What we do now is
It's like a calendar thing.
yes. What we do now is we only keep a snapshot of what the current allocation is, and we only change it according to events. But you're right that if you want to get to out all the performance out of your network, you need to have some prediction, but at least short-term prediction.
And how does A know that it can't, like, when the allocation changes, how does it know that it can't send forward? Is that like?
Yeah, so first you start TCP, and maybe A reacts using TCP congestion control. But the idea is, in parallel to opening the TCP connection, so while the SIM is still flying from C to B, the SIM packet and the SIM app, the C contacts the allocator and tells it, I have a data pending for it. And the allocator crunches this data, and it knows there's a parallel flow from A to B, and it reassigns the rate. So it tells A to throttle down, and tells C it can ramp up, and according to policy. So if ads is more important than Hadoop, which is the case in this example, it would get a higher allocation.
So the allocator has a view of the policy, has a map. It knows that when it goes to flow, it will have essentially the resource of how you see it.
Yes, that's a great question. But you know that might be too much of a detail, but we can discuss that later. Okay, so you'd say, you know, this is great. It sounds very easy. Kind of you change some flows come in, you look at it, and you just reassign the allocation. So let's say, you know, you have this network, and now a new flow comes in, just divide the capacity on these links to that flow, redivide it, and this doesn't really scale. It's really hard to implement. We started out this way, implementing the algorithm. The problem is that these flows share look at this link over there, the left-hand link. So these two flows, the blue and the red one, share that link. So when you allocate resources, you might have to reallocate that link. So reduce the rate of that flow. And now this new flow that you changed, whose rate changed, shares another link with another flow, and another link with a different flow. So these two flows have to change flow very quickly. You have to these updates cascade all over the network. This is a really big problem. And so implementing this way just means
So what kind of routing are you using?
what
What kind of route are you using? I mean, so this is the path
So right now I'm going to assume that I know what path each flow is going to take. How we're going to do it, we should discuss this later. But assume that I know the path.
Yeah, it seems like you might want to reroute maybe a source route.
Right. This doesn't. Ideally, yes, you would want to reroute. Here, I'm just ignoring that.
Otherwise, you're kind of throwing capacity quite possibly.
Yes. Yeah. Definitely, you might be throwing away capacity, but not rerouting. But for the purpose of this talk, this isn't a reroute. So rerouting might be a different time scale and different controller. This is like the fast controller given the path. Okay. In this talk.
You try to learn this as an optimization problem and you can solve it with it can be.
Yeah, I mean, this is what the talk is about. I mean, maybe I need to go faster. Thanks. Yeah, this was really expensive. And the second question is, what goal are we trying to optimize? Are we trying to do the same as TCP? This might not be kind of exactly what everybody wants. We don't want to just share the bandwidth. Maybe we want to give some priority to one user or the other. So what are we thinking about in terms of policy? I mentioned earlier we want to give developers tools to control the network. What would they look like? So this is what I'm proposing right now. This is an example of what you want to do. And it's very intuitive. It's kind of this financial award system where business units come in and tell the network, let's say the base allocation is 1 gigabit for my service. And if you double, and I earn $1, kind of my profit is $1 for my business unit if I get a gigabit. And then if the network is able to double my flow rate for, let's say, Hadoop, I get 5 cents. If I'm ads, like if network doubles my allocation, I get 20 cents. And this translates to these logarithmic utility functions. In general, so this is one example of these utility functions that we can write. So as a function of the rate, what the overall profit from the network is. These are logarithmic, so if you implement this, you get weighted proportional fairness with these constants. But you can have any concave monotonically increasing, strictly monotonically increasing functions and optimize the rate. So I'll show you the algorithms in a second.
How did you come up with these policies? Did you talk with like business units?
I mean, these are, so we actually went to visit this in the other way. Can we try to understand what TCP was doing, and can we do something similar to TCP? And then we found the num framework. This next slide, so great question. So the num framework is the network utility maximization framework, is a framework that optimizes these types of functions. So these are very intuitive, we found when we talked to them. So how does the network utility maximization proposed by Kelly and co-authors in '98? It's pretty simple. It's it has prices per link, prices based on flow rate. So there's a bit of notation here, not too much. So X are the flow rates that each flow chooses. C is link capacity. So you can think about this quantity as how much bandwidth you have and how much flows are taken. So this is demand. And you just price it based on supply and demand. So if demand is higher than supply, prices increases. And the price increases. And if demand is lower than supply, then the price decreases. Very intuitive. And kind of the secret sauce of any of these optimization algorithms is based on this quantity, this difference, how do you adjust your prices? You just linearly, super linearly. This is kind of the secret sauce. And I won't go into what we do, but it's, if you want, it's kind of interesting and it's amazing. Then given prices, each flow chooses a rate. So this is also pretty intuitive. So each flow has a utility function, and we talked these are the same utility functions that I mentioned previously. Then each flow knows what price it's going to pay per gigabit per second, and it subtracts the two. So the utility subtracts the price from utility, and it gets this function, and then every flow chooses the maximum profit. So here, every flow is selfish given the prices, and then the prices kind of make sure that the network moves towards the right allocation. This is an iterative speech. You have to do this more. So this question so far?
So for given quantity of the top, the difference between the and supply, we're going to derive a price, and that price would be the same in the individual function used for any gigabit per second. It's going to stay the same. There's no marginal effect. Until we either change the axis or change the back, and then we'll do and then any gigabit per second is like in the other gigabit per second.
Yeah. So the idea of the price is if you make a link more expensive, the flows with lower utility functions tend to back off more than the flows with higher utility, or in slopes. So that's kind of the signal that the network sends to.
It's going to talk about sort of different flows. Like, well, I want to maximize my utility. And also, members of the business might want to maximize the amount that you pay as a user. You as a user might want to minimize the amount that you pay. And so there's sort of this, and like who wins in this case, and how do you negotiate?
Right. Yeah. So the question is, how do you set prices? I guess, right? Like if I dumb it down, right? Is it a market where everybody has to bid, and if there are strategies to beat this kind of scheme? For this setup, we assume that all of the users are under the same control. So there's a manager of the company, and they wouldn't allow your users to arbitrarily say they would pay $1 billion for doubling their throughput. Right? So it's like all the users have to collaborate to find these weights. You can think about it as if the network operator chooses weights for proportional fairness inside their network, or kind of for the equivalent, right? The scheme that you put on routers. And weighted fair queuing, if you choose the weights for weighted fair queuing, here you optimize globally instead of having these weights per switch. Right, so there's no competition between the users here, but it'll be interesting as
the price here is per link. You do this computation. Is it per link?
this is per link. So each flow. Let me summarize. So this is so the two steps are given rate allocation. Given each flow's rate, you adjust the prices. So you need for each link to sum up all the flows that traverse the link, and then adjust the price. And then given prices, each flow sums up all the price of all the links that it traverses, and chooses a rate based on that. Okay. And so now I want to kind of hand wave how we do this, how we scale this and make this fast. So how do we compute this on the but yeah, we're doing this centrally. So the architecture is you have a centralized controller that gets these on-off events from servers in the network, and so it knows all the flows in the network and knows recompute prices and allocates rates and tells the servers how fast it runs it.
So then you have that.
Specifically suited for distributed implementation. So we do it centrally and then more efficient.
Yeah, great question. Yeah, so couldn't we have done this better with a different algorithm because we have a centralized control? The surprising thing we found, and there might be better algorithms, but we found that num is very amenable for multiple implementations. So you kind of need this distributed architecture of num in order to spread it over. Makes it really easy to compute.
You have to run this every time. There's a new flow for one.
Yes. So, okay, so this is a good question. So do I have to run this for every new flow that comes in? Actually, you don't. So what you can do is you can run the algorithm and then update your data structure with all the new flows that came in and left,
Yeah,
and then run it again. So you have
it's not looking back either, right? It's fine.
yes. Yeah, you just run your algorithm continuously. You have these events coming in, and you update. And I have a slide on it. Just
You're going to talk about like convergence on this result, but it seems to one, there's still this dependence on RTT between the endpoints and the controller. And two is that it may take multiple iterations to converge. If that convergence time is longer than the flow length, then we'll migrate down.
Yeah, that's a great observation. But yeah. Hold off for 3 sides down.
No, no, it's
good. It's good. I like it. This these two representations of the data. You have flow state and you have link state, and this is a very general problem. So many times in networking, you want to look at the flows and then look at the links, look at the flows, look at the links. Why is this a problem when we're trying to do this, to implement this in a multi-core way? So let's say our cores just finished computing step 2. So given prices, each core computed rates for several flows. Let's say for 1 takes flows 1 through 6, for 2, 7 through 12, and so on. And we divide the flows arbitrarily. Now we want to compute step 1. So we take the link number 1, and we look at all the flows that are on that link. We need to sum up all of these rates in order to adjust the price. Then link number 2 has a different set of flows on it. And the problem is that this is really expensive in a multi-core system. So fetching cache lines from different cores is expensive. It takes tens of cycles, 40, let's say, between cores. And usually you hide this latency with a prefetcher. So if you access memory in order, then a hardware component on your core, the hardware prefetcher, gets the data into your cache before you access it. But when you do this random access, so what you really want is something to arrange your computation memory such that you do these sequential accesses. So how do we do this, switching between flow state and link state? So let's drop a network. Sorry, that's slow. Let's drop a network. What we've observed is you can divide this network into blocks. So let's say every 2 racks is a block. So the left 2 blocks are block number 1, then block 2, block 3. If you look at all the links going up from a block, then let's think about which flows can traverse these links. Only the flows going from block 1 to block 2, block 1 to block 3, and 1 to 4. If you look at the downward links, these specifically, which flows can traverse these? The flows from 1 to 4, 2 to 4, 3 to 4, and 4 to 4. An idea of how to arrange the computation, and this is the meat of it. We divide flows by their source and their destination. So here we have a 2-dimensional array, and each cell in the array is a different core. So here we have 4 by 4, 16 cores. Each flow belongs to one of these cells, according to the source and destination. And what we've seen is, let's say the upward link block from block 1, which flows affect these links. So all the flows from block 1 to block 1, which is the circle top left, then all the flows from block 1 to block 2 are in that cell over there, and so on. So block 1 to block 3, block 1 to block 4, and so on. So what you could do is, because you need to sum up over the flows over all those links, what you can do is you can have each of the cores keep a separate copy of the link block, start with an empty one, all zeros, then update their own flows onto the link block. Then you need to take these 4 link blocks and aggregate them together in order to get the link state for the whole rows together. Right, so this is kind of, and for the upward link blocks, you have to aggregate on the columns. So this is the idea. How do you do the aggregation? So each, I'll just repeat. Each core keeps a set of flows, and then when it needs to switch from flow state to link state, you aggregate all those states from flow to the links, and then you aggregate these partial states. When you need to take the global link block state and do that, so for example, you take prices and you need to apply them to your flows, you distribute according to the same mechanism. The way we do this is this aggregation and disaggregation is a communication pattern. It's a very specific communication pattern that is multi-resolution. So you start with blocks of 2 by 2, and you move up link block state to the secondary diagonal on the low link block state to the major diagonal, the primary diagonal. Sorry. Then you look at blocks of 4 by 4 cores. This example is 8 by 8. Just needed a bigger example to show this. And aggregate the link state to the again primary and secondary diagonals, and you do this step again with blocks of 4 by 4 to get the link state on the diagonal. So the nice thing about this pattern is first that it's local. So if you put these small squares of 2 by 2 on the same physical CPU die, it doesn't go between CPU dies, between sockets, CPU sockets. So the first maybe 2 stages don't have to traverse these slow links between processors. And the other nice property is that every core sends and receives the same amount of traffic, which is desirable. And there is no imbalance between the cores. The volume of data.
So that actually like the network is bad.
Sorry, the
network, the cross network is bad.
no, because here it doesn't matter how many flows there are. You transfer the link blocks, and for those you have a regular topology, right? So the idea is each of the cores keeps a link block that is entering, fills it up, and then you just aggregate the link blocks. The link blocks are very regular inside because your network topology. Right? Even if you have 1,000 flows in one of these cells and 100 flows in the other, it doesn't matter how much data you have. Always the entire link block. Cool. That's good.
Is this like a known like hyperlink viewing technique or something?
I'm not familiar with it. This is one. Okay, so this is hand wavy. How does multi-core work? I want to get in the remainder, I want to talk a bit about how this fits. We had a question about, this is an iterative algorithm. What happens if you don't converge in time? So this is the rest of it. Any more questions before we? Okay, cool. Oh, so we ran micro benchmarks of the entire algorithm, the entire noun algorithm on a multi-core machine. It's an 80-core machine at MIT. We used a subset of it, so 4 cores for the first experiment and 16 cores. And if you have we found that if you have under 700, if you have 768 nodes and 6,000 flows, which is kind of a good ratio of live flowlets, then this algorithm works in under 90 microseconds. Crunch out these allocations very quickly. Even if you go to larger networks, you need more cores, but you can scale to 4,600 nodes in under 31 microseconds. And in all of these experiments, the aggregation and the communication between the cores took the majority of time, so more than 50%. So in the big network, it took 16 or 17 microseconds out of the 31 microseconds, which kind of indicates we could kind of use, if we use InfiniBand and RDMA, we might be able to spread it into even more cores. And we don't need a huge machine that's co-located in a supercomputer in order to do this. If we want to scale up, we might be able to.
Yeah, that's a good question. This is so sort of circle orders might be smaller than a large data. So scale it out.
Well, the indication I got from the community is kind of that data centers are operating at 40,000 nodes today and kind of increasing to 100,000 per cluster per pod. So this is where you want the tight integration.
Yeah,
pods
so
is
it's
less important, kind of almost one. Different warehouses, the kind of latency is higher.
that's kind of,
It's still small, but I think so. I believe this can scale for 10x would be kind of reasonable, but sometimes you don't even need that. So if you kind of many companies even don't need clusters that are bigger than this.
like I was just surprised that you charge stocks at
Yep.
4,600. Like, well, how about 46,000? And it doesn't seem, it's one order of magnitude, but that's
Right. I mean, it's always good. But
I mean, did you try
you're
it,
right
or
that kind
is
of
there a
the
reason not
tail
to?
of companies have larger pods, but if you look at the
Yeah, I hear you. I guess my question is, what are the results if you scale that, or have you not done
no, I haven't done that yet. So that's why I'm trying to avoid it. But I think it can be done.
that?
I strongly believe it can be done.
So next question. No.
It depends both on the number of flow. You can work per flow and per link. You have to do both types of work. The work per link is a bit more expensive because at least in this pattern of communication that I described, you have much fewer active cores that do the computation per link than you do per flow.
Actually, we go to the next slide. So my question is that if you forget about the number of nodes, such as the flows and the flows, well, what's the dynamics there? So let's say you have like 1,000 nodes, so if the number of nodes is increasing.
So I think I tried to do this in these three lines. So I kept the number of nodes constant, the number of cores constant, and I increased the number of flows. You have 2x and then I would 2x. It does depend on the number of flows, yeah. But not very strongly. You can quadruple the number of flows and only add.
So this kind of, to me, sounds kind of in the noise because okay, what's the end-to-end time, from like, when I decide I want to start up a flow to when I actually can and when I actually need to do it.
At least in the description I gave so far, it's you start with TCP flow. You just start. You do the SYNAC. You start competing for traffic, and kind of when everything's working correctly, you just get the allocation kind of before you do much damage to the network. So the idea is you have this mice and elephants. Mice should just go through, right? That's the common knowledge.
That's what I'm
So every elephant would get the benefit of the doubt as a mice, as a mouse. So you just like start bursting, like your first 10 packets are free, and then you should get your allocation started forcing while when you're quantitative. That's the idea. No, it's I haven't thought so far.
Seems like
But it's
going to be RTT, there's going to be like diverse software stacks, it's going to be like calculating some stuff. It's almost instantaneous, then propagating all the way back.
the question is, what is the latency of an allocation usually? Is that can I dumb it down?
Well, that's basically it. I mean, I think that's the same question because, basically, you're just sending it whatever your max rate is until the allocation takes effect, right? So that's the question. How much damage? How long does it take? How much damage can you do?
Yeah.
Eventually, the rate
Well, that's another question.
Yeah.
yeah,
So
because you didn't get the
right.
Then you got the right allocation. But the right allocation said 5 rupees. So you didn't send 5 rupees over on the average.
Yeah, I have some experiments with a physical system, but the idea is when you open a new connection, well, I guess it's not true for if you have a live connection. If you open a new connection, then you have the SYN-SYNAC time. So that's a round trip time that you can pay kind of for the controller and to your destination are kind of equivalent. So you just launch it in parallel, and by the time you get the SYNAC, it's already done with your allocation. Oh, plus the computation time. So you have kind of the round trip times cancel out, but then how long is the computation? As long as the computation is on the same order of magnitude as the round trip time, then you don't send more than one window of packets, which is kind of cool.
So,
But you're right that on live flows.
I was going to say, if you look at Synac though, and Synac sent by the OS kernel, right? Whereas presumably this is like an application. Oh, maybe not. Did you run the OS kernel?
But this runs in the operating system. At least our implementation.
You run in the operating system
Yes.
precisely for that reason, so you don't have to traverse like usual.
You don't want to change your applications. I mean, at least we did.
Well, I was just saying your allocator, I guess, if it's some sort of user application, sort of like trying to get to it. And so either it sucks things right up, either sort of, I don't know, it's like there's something that basically owns the interface, and to try to eliminate that additional time. And also you sort of want to make sure that it's not scheduled out. There are all these sort of issues that happen. And I guess my point is that the TCP, like the operating system, is always running, it's never scheduled out. There aren't these boundary traversals and these context switches and all this sort of stuff. So that's, you got to make sure you're sort of comparing apples to apples. Presumably you are, and we're doing that.
So the special machine where you want to have this extreme low latency, and very predictable. Yeah, this is part of the engineering. And we use term. Yeah.
What's the latency of reconfiguring the switches themselves?
You don't need to reconfigure the switches at all. This is software only scheme. So you trust your server to enforce your traffic in this setup. So there's an interesting security question.
That's sort of actually another issue. How are the servers throttling down? Is the application doing it, which actually could be very fast potentially? It have to be done by we need to actually change parameters of like the UTF filter, or we need to use TC, or it turns out that we actually have a switch like the U switch that has bandwidth. There's appreciable time, and it could differ by several orders of magnitude depending on which approach.
Yep. So we try to take the lowest latency approach. We throttle at the operating system.
Oh, the operating system. I didn't say the application.
I mean, you can not the application, but at the operating system. So when you're supposed to send a packet out, you think first before you send it out.
Yeah.
Right. Very good. Okay. So I want to another.
But you do depend on the OS is not going to kernel is not going to keep track of the individual utility functions of 17 applications or 17 containers.
The controller should.
So you actually the contract or what the compatibility of each utility function is application. It's all held in the kernel. So you can have these things on the fly.
Well, and so where you want to keep controller, so the allocator, where you make the decisions on rates. The kernel can just enforce rates. It just gets the numbers, 10 gigabits, 50 gigabits, 3 gigabits, and then the controller needs to map the flow into kind of their utility functions. And this is kind of where it could make it easier to deploy the system, because you don't have to change the applications for the applications that request specific function. You can have almost an overlay. The operating system knows what process is running, what thread is doing the communication, what port it's using. It has this very rich information. It can even record how much CPU this thread has used just before it made the socket call. You can have these crazy kind of metadata that you send out, and then you can map these. You can have these policies that map these into the utility.
So you're saying your rate might actually change depending on which thread is talking to the same piece of input.
You could write policies that you give your threads numbers or names, right? This is my real-time thread, and this is my backup thread. And my backup thread should have lower priority than my real-time.
So that the API actually passes that information all the way down to kernel, so it can enforce the appropriate rate.
I mean, the kernel just has to report all this metadata to the controller, and then the controller maps these into utility functions.
I guess the sort of interesting question is, what the flow is shared by multiple threads. Is it just for that flow, or does it depend on the threads? And, what if there are multiple threads that all send on the same socket?
Yeah, I mean, this depends on how you compose the how you develop these policies. I don't have a language for developing these policies, but if you have ideas, I'm happy to talk to you. Right now, like process and port number, right? What we do today is port numbers, but you can have much richer over individual flows. Okay, so what are the problems with these iterative approaches? Usually, they take a long time to convert. So the traditional wisdom is, let's run this for 100 iterations. And actually, we've measured that 100 iterations is enough. Let's run this for 100 iterations and then output this. So here, instead of 10 microseconds, it takes a millisecond to compute the rate. And this is obviously undesirable. We want the 10 microseconds. We want to allocate within order of magnitude round trip time. So what we tried to do is, let's not run 100 iterations. So the prices between iteration and iteration, the prices between iteration and iteration remains kind of the same. So let's just run one iteration and output the rate. And kind of the network doesn't change that much between updates. So fine. That was what we initially posited. So we ran this. And here, there's an experiment. So on the x-axis, you see the load. So we increase the amount of traffic in the network. It's the distribution of workload that I might talk about later. And then on the y-axis is we count the sum of over-allocation over all the links. So we had, I think in this experiment, 10 gigabit links. So all the sum of flows that are over the 10 gigabits we counted. And in this specific network, you get major over-allocation. Right, because the prices have not adjusted and you're computing based on pencil prices. So your prices are too low, you over-allocate something. So this causes queuing and packet drops, all the bad things. And this is the performance is pretty terrible with this. So this obviously doesn't work. We need to fix it. And the way we fixed it, or we propose to fix it, is by normalizing rates after the optimization. So the rates are the prices are kind of okay, but for the places in the network that have a lot of disruption, so where new flow came in, those are not going to be just right. So here, some links are over-allocated. We can reduce the rates of the flows traversing on these over-allocated links, such that the rates of the flows don't exceed the link capacity. I'll give you the exact details here. So for each flow, we look at all the links on the path. For each link, we compute the flows divided by the link capacity. So how much of this link is over allocated? This could be 1.1, 1.5, or 1 if it's over allocated. Maybe it could be 0.9 if it's under allocated. Then we normalize the flow rate with this largest constant over all the links. So we find the link that is most over allocated, and then we throttle down all the flows proportionally to how much is over allocated. Very simple scheme. What do you think? Globally, for every flow. Okay, yeah, that's where kind of it's not as trivial as you would think. You look for every flow. You look at all the links for that flow and compute that. So this is where kind of usually you would want to, if you can think about taking this number globally, like the link that is most allocated is 1.1, and then follow all the flows by 10%. You do this more gently, and for every flow, we look specifically on its path, what link is most over allocated. And it turns out, I mean, if you look at it a bit, then this throttles all the flows to not exceed the capacity. So you're not going to be as fair as you could, but it's fast, right? So it fixes the network not to have all these bad properties in the couple iterations it takes to heal.
So that assumes that you're going to fix the
even if you don't.
Yeah. Okay.
You do this after every iteration. So you run an iteration, then you normalize the rates. Actually, I have a better slide for this. So this is the architecture. And the servers send the flow that started or ended to the optimizer. The optimizer reruns the engine kind of repeatedly and updates with the flow that starts and end times. And then after every iteration, the rates are copied to the normalizer, which pushes them to the server. And what we found is kind of, there's this graph, but what we found is that you can get 99.7% of optimal allocation, of optimal throughput at least. It's not going to be optimal, it's not going to be completely fair, but you can get very close to optimal throughput. And it's fair enough. I mean, it's fair, more fair than what you get. Some links get underutilized. Maybe. I mean, you do get 99.7, so some have to. Okay, so some NS2 simulations. So we took this kind of almost standard test by now from the DCCP paper, where you have 5 senders and 1 receiver, and every 10 milliseconds you start and you flow, and then every 10 milliseconds you stop the flow. You stop one flow. But in the DCCP paper, the averaging interval was 10 seconds. Here we did 10 milliseconds. Because right in the data center matters, so every millisecond matters. So you can see DCCP is kind of noisy rate. Every color is the rate of individual flow. So here it's kind of noisy. You see the flow sometimes one flow gets more, sometimes the other. This is what flow can get. So I think in this NS2 simulation, within the averaging intervals here are 100 microseconds, but floating converts to the right allocation within 12 microseconds. Fabric is not even geared to sharing the network. It's very kind of single-minded. So, but it does what it does very well. Caudal has a lot of packet drops. So what the application observes from the network is very bursty behavior. The rate allocations are quite fair, but and it only does what it does, right? It doesn't have these utility functions, right? And XCP just takes too long. It has this averaging that it has to do on the network to understand what's happening. So it's pretty slow to react. XCP could be fixed to work better, but I'm going to skip over kind of some of these because I want to get to the last slides and be on time. We ran this simulation with Facebook Workload. They published some of their workload distributions in SIGCOMM, I think, 2015. They had cache workload, Hadoop workload, and a web workload. And we simulated the different amount of control traffic you can put in the network. You can see that kind of under 1.5% traffic overhead as you for these messages, flow it on, flow it off. But considering kind of many networks today, and if you look at the Facebook paper too, their networks are mostly not utilized. So maybe most of the time you utilize your network 20%, and then you have 2 times where you utilize 100%. So this capacity is not even, it's there on the table. You just use it for better.
Well, that's sort of adds some question. You presumably have to sort of prioritize the sort of or maybe you looked at it and said, well, if it does get dropped and you disconnect from your allocator for 20 seconds, you actually find enough good results.
Right. So for this NS2 simulation, this is a good question. So you have to prioritize traffic. So with our previous work, FastPass, we did prioritize these packets. So FastPass kind of allocates individual packets instead of allocating rates. It gives time slot allocations to the servers. Here in the NS2 simulations, and also in the Amazon experiments I'm going to show in a minute, we didn't prioritize the traffic. So we just allocated enough headroom for the mics and considered the control traffic. So they usually went through without queuing.
Yeah. So queuing delay seems to
yeah. I mean, this result is after. Well, I guess this result is after queuing delay, but this setting might not exhibit the queuing delay you would see for a loaded network with low distribution. But we still get good results. So I'm not going to show it, but there's some in the paper. And we get much better at 99 than all of these other schemes that we compare to. I don't have time to show it, but I can send you the replay. I'm gonna jump ahead to talk about the Amazon experiment. So we implemented the controller kernel modules for Linux, and we got 10 EC2 machines. These are the extra large machines where you have 10 gigabit. So see it goes to 10 gigabit. And we ran a similar experiment to what, so we had 10 machines, we had 8 senders, 1 receiver, and 1 controller. So when we tried regular TCP, we just didn't use the controller. So same setting as before. You start at some TCP, so you start the connection here we did 15 milliseconds because averaging intervals of 100 microseconds are the kernel is too noisy for 100 microseconds. We did 1 millisecond averaging interval. So we had 50 milliseconds between different flows coming in, and then we peel off one by one. So the baseline is extremely noisy. This is kind of Ubuntu with a recent kernel, cubic TCP. You can see that when you have more than 3 flows, the rate allocation is chaotic. So it's not fair, basically, in these times. And then with FlowTune, you get what you would expect. This is the equivalent. And here, kind of, I didn't even put all the servers into a placement group. So there's the Amazon network in between. So the next test is kind of response time. I said that, I started the talk by saying response time is really important in the data center, and we need to reduce it. So here, the workload is kind of interactive analytics. You're using Spark, and you're querying your data set interactively. The workload is you have these 8 senders. Each one of these has 10 worker threads that send 10 megabytes to the receiver. And what you care about is when you get the last byte, so co-flow completion time. So you want to display kind of when you get the results to your screen as when you get the last byte. This is, by the way, the x-axis here is not 0-based, so it just makes it easier to read. I have to tell you in order to be honest here. So the baseline TCP has a kind of a long tail. So this is a very kind of isolated incident where really networks are very much more noisier than this, right? You have a lot of these Spark queries competing, and you have different services competing on your network. This is very isolated. And here you can see that kind of in many cases, the transfer takes a lot more than it should, right? It has a long tail. With FlowTune, just doing fairness. So here we have your policy is the same amount of the same utility function for all the flows. Just getting fairness between the flows gets you a huge reduction in co-flow completion time. This doesn't even take into account co-flow. You could, with the same architecture, you could allocate based on co-flows. Here, just fairness gets you 1.6x reduction in 95%. Right, yes, so it's like per flow. It's agnostic to what's happening, but just getting better fairness. So I showed you the TCP, kind of how noisy it is. Just getting better fairness gives you much, much better results. And we believe we can do it better than this if we take into account.
Was this a one burger thing or?
I don't know, it was an Amazon. I assume, no, so I would posit that the bottleneck link would be between the top of rack switch of the receiver and the receiver.
Yeah,
I'm not sure if there would be other bottlenecks in the system. This is geared towards showing just this one bottleneck.
Yeah, okay. So then the rate is simply like it's easier to calculate than if we had anybody. I don't know how
yeah, but it's the same algorithm. And
yeah.
it computes as if you had as many as kind of it actually has the same cost whether you kind of it's very simple.
That's almost what I don't understand about the EC2 simulations is, you don't know your network topology, you don't know what the links are, so how do you model it? So is your model just this degenerate model where you assume that you have 10 virtual links all fitting with this kind of switch?
Yes, one big switch.
That's it's surprising that this as well as it does then.
Yes, surprising, right? But it does. TCP is terrible. We need to do better. We need to do much better, and we can do a lot better.
Yeah, and presumably if Amazon could actually maybe give you a virtual networking topology,
you can query it. You can kind of trace route and understand and kind of figure out the network for yourself. You wouldn't know the link capacity.
Doesn't tell you about bridging. Right, which is what you care about.
Thank you. Yeah, but you know, even now, just making sure that the bottom is kind of the bottom layer of your network, kind of just the connection between your edge, but your servers and the top of rack switches.
Yeah, that's
Just
what this,
making sure that is not over allocated.
that's what this says. Basically.
Yes. I hope I've shown you a network scheme that where users can explicitly say what they want the network to do, how they want to behave. They don't specify the algorithm per se, but they specify the policy. And the network automatically enforces that policy and quickly and consistently. So there's no luck to which flow and it's a software element solution, which makes it very easy to do. And with that, I hope we could all kind of work together to give our application developers and DevOps the tools they need in order to communicate, to control the network. Right now, we have this separation between the application developers. They use TCP and they care about how do they scale their deployment, their deployment cycles, kind of DevOps. And the network engineers care about latency, throughput, and kind of routing, just establishing the infrastructure. We need to bridge this gap. We need to have the application developers be able to specify the policies, kind of how they want the network to behave and how the performance should be on their network. Ideally, self-service. Everybody logs in or marks their service with what communication properties they want. So I'm hoping, I'm really excited about this goal, and if you have more ideas in this area, and I'm happy to take more questions. We had a lot, so I guess we'll have. Do we have time for another one or two, or do we want to?
Yeah, maybe we should take it offline because we're a little over time.
Yeah. So thanks everyone for coming. And I'll be here for.
So you have to run this work on that.
This is a technical corporate.